Hello and Assalamualaikum everyone. My group and I will represent our case study on capacitive touchscreens as part of our electromagnetic assignment. This project explores the challenges faced by these essential technologies and provide innovative solutions based on electromagnetic principles.
This is how capacitive touchscreen work. First is self-capacitive touch sensor. It's using a single electrode of the capacitor, measures the degree of change in capacitance based on ground. When we touch, the capacitance will increase. Next is mutual capacitive touch sensor. It using both electrodes of the capacitor, measure the change in capacitance between the two electrodes. When we touch, the capacitor will be decreased. Multi-touch is possible, but the detection algorithm become more complex.
My name is Fazi. I will start with the introductions. Capacitive touchscreen have become an integral part of our daily life, powering devices such as smartphones, tablets, and even industrial systems. Their widespread use can be attributed to their intuitive interface and reliability. However, as we expand their application to more demanding environments, they face three major challenges. The first one is electromagnetic interference, or we call as EMI. This strips the electrostatic field that capacitive touchscreen rely on, leading to false touch response and reduced accuracy. Second challenge is conductivity limitation, where touchscreens struggle to detect non-conductive objects like glove or plastic styluses, making them difficult to use in specific conditions such as cold weather or medical settings. Lastly, signal noise, originating from power supplies or environmental interference, further reduce the precision and responsiveness of touch input. In this study, we aim to address these three challenges by leveraging electromagnetic principle and proposing solutions such as EMI shielding, improved material, and adaptive signal processing. The next part is fundamental concept. To understand these challenges, it is important to look at the fundamental concept that governs capacitive touchscreen. This screen operates based on the interaction of electrostatic field. When a conductive object like a finger comes close to the screen, it alters the electrostatic field, which is then measured to determine the touch locations. However, external electromagnetic interference can distort this field, causing issues like false touches or lack of response. This is where electromagnetic shielding comes into play, using materials to block external interference and stabilize performance. Another critical concept is capacitive and conductivity. Conductivity materials such as metal or conductive polymers enhance the interaction with the touchscreens. Non-conductive objects like gloves pose a challenge, but innovative solutions involving conductive coating or fiber can help address this. Last but not least, signal integrity is also essential. Noise travel from supplies or in the environment can interfere with the touch detection. Techniques like low-pass filter and adaptive algorithms are employed to maintain signal integrity. Ensuring precise touch input, advanced material science also play a key role in improving durability and sensitivity while balancing transparency and flexibility in touchscreen design. For the theoretical foundation, capacitive touchscreens are built on several electromagnetic principles. The first one is Gauss' law, explain the relationship between electric field and enclosed charge, which is essential for analyzing the electrostatic field used in touchscreens. The next one is Faraday's law of induction, describe how changing magnetic flux can induce current, helping us understand how external field impact touchscreen circuit. The capacitance formula, which defines capacitance based on permittivity, area, and distance between plates, is critical for optimizing touchscreen sensor. Next is Ohm's law, help us understand through the role of the material conductivity in touchscreen performance, while Maxwell's equations explain wave propagation, which is vital for modeling EMI interaction with shielding materials. Next, I will pass this presentation to my next members.
Electromagnetic interference, or EMI, is one of the key challenges faced by capacitive touchscreens. EMI occurs when external electromagnetic fields disrupt the electrostatic field used for touch detection. This can result in issues like false touches, ghosting, and reduced sensitivity, especially in environments with high electronic activity. For example, industrial settings with heavy machinery or proximity to devices like Wi-Fi, routers, and CPUs often generate electromagnetic interference. This affects the precision of touch inputs, causing inaccurate or delayed response. MI pose a significant challenge to the usability and reliability of capacitive touchscreens in these demanding environments. Address the challenge posed by EMI. We propose EMI shielding as a practical solution. This involves using materials like transparent conductive films or fine wire mesh to block external electromagnetic interference. Transparent conductive films, such as those made from indium tin oxide, are applied through high vacuum processes to create dense and durable coatings. These films stabilize the electrostatic field, ensuring accurate touch detection even in high EMI environments. Fine wire mesh, typically made from stainless steel or copper, is another effective shielding material. It forms a conductive grid that blocks interference while maintaining optical transparency. These materials are essential for improving touchscreen reliability in environments with significant electromagnetic noise.
Another major challenge faced by capacitive touchscreen is conductivity limitation. So the screen works by detecting change in the electrostatic field caused by a conductive object such as human finger. However, the non-conductive object such as glove or a plastic stylus do not alter the electrostatic field in the same way. This will make the screen unresponsive to this material, make it difficult in a certain scenario. For example, in cold environment where gloves are necessary, or in a medical setting where protective barriers are used. Capacitive touchscreen become less practical and versatile. So, to overcome the conductivity limitation, we suggest integrating a conductive material into the non-conductive object. For example, by using a silver-coated fiber or graphene coating in glove or a stylus. So this material will mimic the electrical properties of human touch by creating a small capacitance at the point of contact. This allows the screen to register the input as if that were a human finger. So by using this conductive enhanced material, touchscreen can effectively operate in the environment where direct human touch is not possible, such as in the cold weather or in the medical setting. So this solution can ensure for better usability and versatility across a various scenario.
So next I'm going to talk about the third challenge with capacitive touchscreen, which is signal noise. So what is signal noise? Signal noise is unwanted electrical signals that messes up how your touchscreens detect your input. If you ever had a touchscreen freak out, registering the touches that you didn't make and not responding to your inputs, so yeah, that is the signal noise causing problems. So what makes it happen? There are a few key points here that I will talk about. The first one will be capacitive coupling. Now this happens when external electrical fields interfere with how the touchscreen measures the capacitance. Now these fields can come from things like nearby electronic devices or even environmental changes. The interference will disturb the signals and make the screen think that there's a touch when actually there isn't. Next, I'm going to talk about the electromagnetic interference, or also known as EMI. Now, EMI comes from devices like motors and wireless gadgets. These devices will create electromagnetic waves that will overlap with the touchscreen's signal and will cause the device confusion. For example, when you're using your phone near a heavy machinery or a crowded area with lots of wireless activity, now this can trigger the issue. And lastly will be the frequency overlap. Now this happens when the noise sources operate at similar frequencies as to the touchscreen. So when the frequencies align, the noise will blend into the actual signals, which will make the SNR, signal to noise ratio, become lower. Now this will make it harder for the touchscreen to tell the difference between a genuine touch and an interference. So why does signal become a challenge to capacitive touchscreen? First of all, there are impacts to users where, for one, you get false touches, where the noise mimics actual signs and the screen will think that you actually touch it when you didn't. And the second one will be missed inputs. Now this is super annoying when you are trying to type or scroll on your phone or on your iPad. And on top of that, the devices might use extra power to compensate for all of this noise, which will then lead to faster battery drain. The solution for this challenge is adaptive signal processing. So adaptive signal processing is where the device will learn to tell the difference between actual touch signals and noise. So there are some key features. The first one will be dynamic adjustment. So dynamic adjustment is where the system will constantly monitors the environment so that it can adapt to any kinds of changes like if the noise levels suddenly spike because you are using your phone in a crowded space like a cafe or just being near a big machine. This will help you have a better performance without you needing to change anything. Second is the enhanced SNR. Now this will use filtering techniques to clean up the signals by analyzing the patterns in frequency and amplitude. So by boosting the SNR ratio, it will make sure that the real touches, genuine touches, are being detected more accurately while the noise are being filtered out. The third one is machine learning integration. So the system can learn from past experiences where it will figure out how to take out the repeated interference sources automatically. For example, if you are always using your phone in a noisy environment, it will adapt and improve the performance over time. So there are some benefits that you will get from all of this. One of them is that you will get more accurate and reliable touch detection even in a noisy environments. It is perfect for all sorts of applications from smartphone to industrial settings. And most important of all, the users will have satisfaction and be happier. So yeah, signal noise can be a burden, but with tools like adaptive signal processing, it will be manageable.
Next, we go to the conclusion. Capacitive touchscreen are an indispensable part of a modern technology, offering seamless and intuitive interfaces of various devices. However, as we have seen, these technologies face challenges that demand continuous innovation. Through the case study, we identified three key challenges, which is electromagnetic interference, conductivity limitation, and signal noise. Each of these challenges present unique barriers to performance and usability. By integrating theoretical knowledge with practical engineering approach, we propose solutions to address these challenges effectively. This innovation demonstrates how engineering and theoretical principles can work together to solve real-world problems. By enhancing the reliability, precision, and versatility of capacitive touchscreen, we can expand their application across consumer, industrial, and medical domains. This innovation not only enhance touchscreen performance, but also ensure that reliability in diverse environments, from industrial setting to medical application. This study highlights the importance of bridging the gap between theoretical knowledge and real-world application. By doing so, we can develop technology that remains user-centric, adaptable, and reliable. Overall, this project has reinforced the critical role of engineering in solving complex technological challenges through creative and practical problem solving. In conclusion, capacitive touchscreen face challenges that require continuous research and development. By addressing these challenges, we can ensure that this vital technology remains a cornerstone of modern devices while paving the way for a more connected and innovative future. Lastly is reflecting on this case study. It is clear that capacitive touchscreens have become an essential part of modern devices. However, their functionality is often constrained by environmental and material limitations. Through this study, we combine theoretical principles of electromagnetic with practical engineering solutions to explore innovative ways to overcome these limitations. By understanding concepts such as electrostatic fields, capacitance, and electromagnetic interference, we were able to identify key challenges and propose effective solutions. The integration of advanced materials, adaptive signal processing, and EML shielding techniques demonstrate the potential to address these challenges.